Welcome to the AI Research Roundup. I'm Alex. Today is May 11th, 2025. We're looking at an ICLR conference paper, EmbodiedSAM, online segment Any 3D Thing in Real Time, published January 22nd this year, so just under 4 months ago. This paper presents EmbodiedSAM, or ESAM, a system for 3D instance segmentation. That's about AI agents identifying and outlining individual 3D objects in real time as they explore. It cleverly uses powerful 2D vision foundation models, adapting their insights for 3D by processing live RGB-D video, which is video that also includes depth information. Alright, so this first figure really sets the stage, comparing EmbodiedSAM's approach to previous methods. On the left, older systems process RGB-D video offline. They use a vision foundation model called SAM, that segment anything model, to get 2D masks or object outlines. These are projected to 3D and slowly merged. The figure shows this achieves an average precision, or AP, of 20.2. Average precision is a score for object identification accuracy. Higher is better. EmbodiedSAM, on the right, uses streaming video. It also starts with SAM for 2D masks, but then cleverly lifts these into 3D queries. Think of queries as smart object descriptors, and refines them. This leads to much faster and more accurate 3D segmentation. Okay, so this next figure, figure 2, gives us a look under the hood at the EmbodiedSAM system itself. It starts with the posed RGB-D input. That's the video stream with depth, where the system also knows the camera's viewpoint. The segment anything model, or SAM, generates 2D masks. Then, the query lifting stage is crucial. It doesn't just project these 2D outlines. It creates 3D superpoints, which are like smart clusters of 3D data points, and uses geo-aware pooling, a method that considers the actual 3D shape to turn them into initial 3D queries. These queries are then refined by a query decoder, and finally merged over time to track objects. So, following how those 3D queries are refined and ultimately merged, Figure 3 here details that efficient merging strategy. It employs 3 auxiliary tasks, which are like specific helper training goals, to make the object descriptions really distinctive. There's a geometric task for overall shape, a contrastive one for telling different instances apart, and a semantic one for object categories like chair. These tasks help generate unique numerical summaries or vectors for each object. The system then efficiently compares these vectors, prunes less likely matches, and uses bipartite matching, an algorithm for finding optimal pairings, to consistently track objects across video frames. Alright, so after understanding that efficient merging, this table, Table 2, highlights the system's generalization, how well it performs in new environments. It details, quote, dataset transfer results, taking models trained on ScanNet 200 and testing them on CNN and 3RScan. We see scores like the overall average precision and also AP50. AP50 is average precision, where the prediction must have at least 50% overlap with the actual object, measured by intersection over union, or IOU, quantifying how well predicted and true areas match. EmbodiedSAM consistently achieves strong scores here, showing it adapts well. Building on that strong generalization, this table, Table 1, now focuses on core performance on the ScanNet 200 dataset. It compares methods for class-agnostic 3D instance segmentation, that's identifying individual 3D objects without knowing their specific type. We see metrics like overall average precision, AP50, and also AP25, where AP25 is average precision, requiring at least 25% intersection over union. EmbodiedSAM Online achieves 42.2 average precision, with its own processing adding just 80 milliseconds. The ESAME variant, using FastSAM, reaches 43.4 average precision and a total frame time of only 100 milliseconds, significantly faster, highlighting its efficiency. Following that detailed performance on ScanNet 200, Table 3 now broadens the view, showing 3D instance segmentation results on both ScanNet and CNN datasets. We see the familiar average precision, AP50, and AP25 scores alongside frames per second, or FPS, which measures processing speed. The ESAM plus FF variant, for instance, which is an online method, achieves a strong 42.6 average precision on ScanNet and 33.3 on CNN, all while processing at nearly 10 frames per second. This really underscores its capability for real-time operation, a key advantage over offline approaches. So to wrap things up on EmbodiedSAM, it's clear this work makes significant strides in real-time 3D understanding for embodied AI, which are AI systems designed to interact with the physical world. The key here is how it cleverly uses 2D vision foundation models. These are large AI models pre-trained on vast amounts of visual data for fast and accurate 3D object identification without the heavy offline processing. This really opens doors for more responsive and aware robots and agents. That's all for this AI Research Roundup. Thanks for tuning in.